Okay. Yes, all four of these would work just fine. Sorry, all three of these work just fine. That last one, I don't like you, but that's okay. Okay, positives.
133.
133. That's perfectly fine.
493.
493. Anybody go much higher than that?
What about you, Scott? I'll go much higher.
Of course you would.
That's not high enough.
All right. Then the reference angle.
No, I got a good one.
I'm not listening anymore, Scott.
It's 70,000.
Tuned you out, Scott. All right.
Reference angle. It's not as bad. 47.
47. It is correct. It is in the second quadrant, so we can do 180 minus the angle. 180 minus 133 will give you 47. It is also 47 degrees away from the axis, no matter which one you're on. This would be correct. Any of these negatives, any of these positives, and that reference angle would be good. Second one, pi is this time. 48 pi over 5. Negative 2/5. That'd be a good one. That'd be a negative. Do we have anybody go any more negative besides Scott?
I did.
Thank you. Any others? Okay then, positives. 38 pi over 5 would be good. Others? 28 pi. 8 over 5 pi. All those are good? Alright. Now the magic number. The reference angle.
0.5.
0 over 5? Yes. Negative 12 pi over 5 would be just fine. Now, you said 3 over 5? That is incorrect. It is 2 pi over 5. Now, let me explain. We talked about this yesterday, right? We have over here, as our option, 8 pi over 5, or I'm going to use this one, negative 2 pi over 5.
Okay.
So, negative 2 pi over 5, it's negative 2 pi over 5. So remember, this would be negative 5 pi over 5, because it's 1 full pi over. So this would be half of that distance, so 2.5 pi over 5. So negative 2 would be down here in the fourth quadrant. And so it would be 2 pi over 5 as our reference angle. Alternatively, 8 pi over 5 is also in that fourth quadrant, so you can find it the same way.
Wait, that's in the fourth?
It is in the fourth quadrant.
Okay, that's where I messed up.
That is where I messed up. Yep. It is in the fourth quadrant. 8 pi over 5. That is a great way to do it. So remember, there are 4 locations on the unit circle that matter a lot. 0, pi over 2. So, 0, pi over 2, pi, 3 pi over 2, and 2 pi. You want to figure out where your number sits in these numbers. So if I look at 8 pi over 5, I can convert that into a decimal. And I can convert all 4 of these into decimals and see where it fits in. Pi is 3.14. Pi over 2 is 1.77. 3 pi over 2 is 4.91. And 2 pi is 6.28. So if you were to take 8 pi over 5, type it into a calculator and get a decimal number, you'd find that it's just a little bit bigger than 4.91. It's about 5.03, I think. And so you can clearly tell it was in the fourth quadrant because of how the numbers fit. And that's much easier to do when it's in degrees, because it's much easier to see how they fit together because they're easier numbers. What was the number actually? 5.02. That's pretty dang close for us. Okay, so you can clearly see it's going to be in this quadrant because it's clearly bigger than 4.91 but smaller than 6.28, so it's definitely in quadrant 4. Now, if you're a calculator, that's real helpful. If you don't, always have the fallback plan and just convert it to a degree. 8 pi over 5 as a degree would end up being, let's see, can't do it in my head more. Get hold. 298 degrees. which would clearly be in fourth quadrant. So, any of these are great techniques to approach. It works fine. You've got to figure out where this place is and figure out how to find the correct formula to get to our solution, especially for the reference angle. That tends to be the hardest one once you get used to this process. Because I have to start 2 pi, that gets the old hat real quick. I can start 360, pretty straightforward. It's this reference angle that causes the most trouble consistently, especially with the radius. So your options are convert it to degree to make it a little simpler, or get real comfortable with knowing those values as numbers and be able to compare them. If you get real good, you can compare them as fractions without converting them to decimal. If you want to get really good at trig, that would be your long-term goal, is get comfortable with fractional math. That's stuff from like 3rd grade, and 5th grade, and 7th grade, and 9th grade. That's stuff that people still struggle with when they leave high school. Okay? If you can get comfortable with that, trig can become easier. A lot easier. Let's talk about today's stuff. For today's material, we're talking about the Pythagorean theorem, which we've mentioned already once in this class, and specifically its use when it comes to trig ratios. Now, from our quiz, there were no problems that asked specifically about the Pythagorean theorem, but there were a number of problems that use the Pythagorean theorem to assist you on this thing. If the problem mentions trig ratios for your problem, you will end up using the Pythagorean theorem 9 times out of 10. Remember, trig ratios are just those 6 formulas on the board up there under the right-hand side on the Holy Grail. Sine is equal to opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. These are meant to be starting places for future trig problems. The more advanced problems we had on our quiz, when it had the most trouble, like numbers 10, 11, and 12, where I give you a triangle and ask you to use some trig function with it, those are far more typical where you're using a trig ratio combined with other math. If you take the trig ratios down first, that's the problem. So, let's start off with by talking about Pythagorean's theorem. 2 versions. A squared plus b squared equals c squared. The one every geometry student knows. Yay! In this picture, it's important to note the locations of the pieces. A and B are the 2 legs. C is the hypotenuse. Now, as we get more confident with the trig part of this, I start to adjust using the alternative formula, which is the same idea, but instead using our trig sides instead of our geometry sides. Our trig sides are always in reference to an angle. So when I draw my picture, I will have to have an angle in here as well. Here we go. Here's my picture. The angle in question I'm going to call theta, like it's standard in trig. Opposite is always across from, adjacent, next to, hypotenuse, the longest. Note these are the same pictures, same basic problem. They have the exact same numbers. The formula doesn't change. The Pythagorean theorem is cool that way. Now, check the Pythagorean theorem. You gotta have the right components. Okay, get on that. You gotta have the right components. You gotta put them in the right spot. Most common mistake with the Pythagorean theorem is to put something in for A when it should have been for C, or vice versa. Details have to be assistant when you look at a problem. Here's the picture. Be careful and identify the sides. Ask which side is the hypotenuse. The hypotenuse is king, or queen, or empress, or pope. I don't know what your feelings are about modern history. It's the big one. It's the one that has to be fully fixed. C, H, the 2 that have to be in the right spot. A and B, O and H can be flip-flopped. They won't change the math at all. But C has got to be correct. H has got to be correct. Now, how do we use this? Primarily, to solve trig ratios given a trig ratio. Now, problem with this includes when you're given a single trig ratio and have to find both the other ones. As was on your quiz. Example. I have the following problem. Our first example on the day. We know that cosine of theta is equal to 3 over 7. And I tell you to find all other trig functions. I thought find all and I put fall. Find all other trig ratios. Now, as a reminder, Every trig ratio has a natural inverse, opposite, which is easiest to find first. The opposite of cosine is secant. So if cosine is 3 over 7, secant will be 7 over 3. However, the other trig ratios can only be found using Pythagorean's theorem. So I will begin this problem, as I begin many others, by drawing a picture with what is known. Now, as I mentioned in class, you can draw the same picture every time, which I often do. There's theta, there's A, there's O, there's H. It does not matter. As long as you get the pieces in the right spot. If you have to know all your trig functions, very well. Cosine, adjacent over hypotenuse. So that means that this 3 is not a 3. It's reflective of the adjacent side. This 7 is not a 7. It's reflective of the hypotenuse. So in this picture, 3 over 7 would mean that the 3 goes here, and a 7 goes there. If I want to do the other trig ratios, I can actually do them at this moment. I just end up with something that I can't fix. Sine would be opposite over hypotenuse, so it would be O over 7. That's an issue. I don't know what O is. Tangent would be opposite over adjacent, so it would be O over 3. I don't know what O is, so I'm stuck. At any point in time, I could start doing the trig ratios. Don't fool yourself. You could start right now. The issue is, I don't know what one of the sides is. So doing the trig ratios just means I get stuck very quickly. I find this inside. Pythagorean's theorem. O squared plus A squared equals H squared. O squared plus A squared equals H squared. 3 squared is 9. H squared will be 9. O squared. Subtract 9 from both sides. O squared equals 40. Take a square root of both sides. Now, you can either simplify it at this point in time, the square root of 40, or you can leave it until later. I prefer to leave it, because remember, I'm going to use tricks to find all 6. I'm going to use inverses to get them quickly. Okay? Knowing and being comfortable with all 6 trig functions, how they fit together, makes you faster. Sine, theta, cosine, theta, tangent, theta. And their opposites, cosecant, theta, secant, theta, cotangent, theta. Let's do it. All right. The one I started with was cosine, which was 3 over 7. The one I'm guaranteed from the beginning is secant, 7 over 3. Those are so far so good. Now let's fill in the rest. Sine, according to my picture, sine is supposed to be opposite over hypotenuse. So in my picture, opposite is square root of 40. Hypotenuse is 7. So sine is square root of 40 over 7. I will not grab my calculator out just yet. I'll go ahead and do the inverse. The inverse is the flipped. So 7 over square root of 40. Cosine's done. Tangent, opposite over adjacent. So square root of 40 over 3. Cotangent, square root of 40. It's only when I get them all down that I go ahead and have to plug them in anytime or simplify them at any point. First one, sine. Square root of 40 is 4 square root 10 over 7. That's a lie. I'm stupid. Douglas. It's Tuesday. It's Thursday. I don't even know what day of the week it is. 2 square root 10 over 7. Set it with the square root of 40. Let's see. That would be equal to 20 over 70. That seems wrong. 7 square root 10. There we go. Leave these as fractions. Tangent, square root 40 over 3. That would become 2 square root 10 over 3. Again, calculator's your friend. And then cotangent, 3 over square root 40. That would become 3 square root 10 over 20. The middle two are fine because they're already simplified as best they can be. Done. Finding all 6 trig ratios using 1. Big detail here, making sure to have your right components going into your picture, making sure your picture is set up correctly, using your Pythagorean theorem correctly, simplifying the Pythagorean theorem correctly, and then plugging back into your trig ratios correctly. At any point in time, you may do a trig ratio. A trig ratio is just a relationship between two sides. The trick is, a trig ratio is only really useful if those two sides are known, or is a variable that I want to use somehow. At any point in time, the trig ratio fits this. Now, something we didn't mention heavily, but I want to make sure it's very clear because this posed a significant issue with some of the later problems. Because there was a clear mismatch in understanding. Cosine is 3 over 7. That does not tell you what the triangle is. I told you the triangle has sides of 7 and 3. That is actually a lone triangle. It could be 7 over 3. It could also be 70 and 30. Because when they reduce down, they have the same relationship. Remember, a trig function only describes a relationship between the sides, which could be simplified. We could have 70 for the hypotenuse, 30 for the missing side. We could times both sides by 2. We have 14 and 6. And the cosine wouldn't change, because when you plug it all in, when it's simplified, it'd still be 3 over 7. I don't know that this is the right triangle. I know this is a good triangle to describe this relationship. It's the easiest triangle to work with. If I wanted to, I could do 14 for the hypotenuse and 6 for the adjacent, which does reduce down. But if I did, when I do Pythagorean theorem, I'm just doing with bigger numbers, I'll eventually reduce the same answers I would have gotten doing it with these numbers instead. Trig ratios are designed to provide the relationship. They never tell you the triangle itself, only the relationship. These two sides could be something ridiculously nasty. As long as that nasty thing simplifies to 3 and 7. That's all that matters. The trig ratios do not define the triangles, they define their relationship. Another example. I know many of you guys already have this part. You guys didn't have a problem at all with this on your guys' quiz, so I'll give you guys plenty of time to work on homework and make sure you get done before you leave. So, next example, we'll do it quick. Example. Let's use a different trig function. Let's say cosecant of theta is equal to 30 over square root of 197. What a cap. Yes, ma'am. At any point in time, I can start doing trig ratios. So I'll actually start this problem by writing down the 6. The thing is, one of the sides is going to be missing, so eventually I'll need to fill that in. So this is an alternative method. If you like it, you may choose to follow it. If you don't, it won't ruin anything. It's just a different way of doing it. In this case, there's my 3. And then I have cosecant, secant, and cotangent. Okay. It is likely this will be nasty. It does not change the process, it does not change the problem. Let's talk. Okay, the ones we know. We know cosecant is 30 over the square root of 197. That means I already know that sine is square root 197 over 30. One answer is done, 4 to go. And I actually know a lot about this problem. Example. Because of how cosecant is constructed, h is on top, o is on bottom. All these trig functions contain either h or o or a, a combination of 3. I can fill in most of this and just leave some blanks. Here's what I mean. Cosecant. The top number is the h. In cosine, the bottom number is the h. What's the top number? Don't know yet. I know it's going to be there. On secant, the top number is the h. If I can find out what O is, if I can find out what A is, I can just plug it in and I'm already done. What was I simplify? On tangent, the top number is the opposite, which on cosecant, the bottom number is the opposite. So we have square root of 197 right there. Cotangent, square root of 197 on the bottom. This is an alternative technique. Works pretty well. As long as I can find that missing side, done. Just plug it in. Now, looking at cosecant. The top number is 30, the bottom number is the square root of 197. I got to think Pythagorean's theorem. How would that plug in? To plug in Pythagorean's theorem, I either need H or need A and B, or whatever combination you choose. 30, square root of 197. Tell me more about how would they fit into Pythagorean's theorem. How would the 30, square root of 197 fit into Pythagorean's theorem?
O squared plus 1 square root of 9. No.
It would be
That's confusing.
square root of 30 minus, well no, 30 squared minus square root of
Very
9.
simplified. Okay. I liked where you were going with that. Mentally.
Well, I was.
Keep going. Think it through. Think it through. Okay.
How do you
Which number is your O? Which number is your A? Which number is your H?
197 would be
197 would be an A?
no. Would be
Oh.
Oh,
And the 30?
30 stop.
Okay. So this is an option. Instead of drawing the picture, I can just start thinking about, okay,
Equals 30 squared. Or square root. Squared.
I can start thinking just where does it go in the theorem?
I see, no.
Because remember, I can just straight plug and chug straight into the theorem. I don't need the picture. The picture is only helpful to get me to the theorem. But I don't need the theorem at all. I don't need the picture. Because that thing up there tells me how to put it into our version of Pythagorean's theorem. Cosecant is H, so 30 goes over here. 197 is O, so 197 goes over there. It's just an alternative way. Like I said, and some of you will pick up the quick and be like, okay, this is easier, I can do this. Some of you will be like, I'm just going to do it, all the steps, and I'll be fine. Like I said, I'm not a fan of telling you which direction to go. I want you to have your own paths. So find a path that works for you. All right. 30 squared. Square root of 197 squared. Those two I need to know. 30 squared. 900. Remember from earlier in the year, squares and square roots cancel. I mean, I get 197 plus a squared. And subtract. Getting rid of the 197. A squared is equal to 703. Take a square root of both sides to get a by itself. So a is the square root of 703. At this point, I can actually just plug in a into my 4 equations that I have left to do, and I'm actually done. I just have to simplify what I can. So cosine, remember, is a over h. My a, square root of 703. Tangent is o over a. So square root of 703 we go on bottom. Secant is h over a. Square root of 703 we go on bottom. Cotangent is a over o. Square root of 703 on top. As long as I simplify what I can, I'm actually finished. Now this first one is good. 197 does not have a square root. The second one is actually also good. Square root of 703 does not have a square root. Tangent is not quite nice, and it gets nasty when you plug it in. So please do that.
Can you just leave it as a decimal, or do we have to?
I'd like it to stay as a radical if I can.
Calculators don't like that.
Calculators don't like it?
I'm just gonna do 7 over the square root.
Yeah, why'd you put it?
So, if the calculator is giving you heck, leave it there. I'd rather you left it there
Because that's right.
than put it as a decimal. Because that's probably your decimal place. Okay, if you have to choose, leave it. Okay? I'm sure the same kind of thing probably happens over here. Now secant, I can do that one. That's 30 square root 703 over 703. And cosecant was given to us in the problem, so I assume that's good. I'm not going to fix the one they gave you. If they wrote it that way, you won't get that. So there are 5. When it was given, here, left the way it was, and the 5 have all been simplified according to our rules, as far as we can take them. Again, 30 against power 197 could be the two sides, or they could be a relationship that simplifies those two numbers. Probably an ASCII one, so an ASCII numbers, but that would still work. Never let that get in the way of how the math proceeds. Here are your 10 problems for the day. Let's throw them up here.
I hate these problems so much.
Good.
So much work.
Let the hate.
We just
Flow
do on
through
the
you.
paper we did the work on.
Yes, please. I'm on the same paper you got the bell work on. 7.
How many are we doing?
These are a little longer. You do take up a lot more paper. You know what? I'll stop at 9. I'll be a little
One,
nice.
sweetie.
Yeah, me too nice. Alright. Let's do them. Sine. Cosine. Tangent. Cosecant. Secant. Cotangent. And what are the two that are most commonly frustrating? Let's do one tangent problem
Oh, yeah. Those are the easiest, to be honest.
and sine problem. Okay, let's put the numbers up here. Alright, try to keep the first couple nice. Let's see. Sine, let's make it feel nice. 4 over 5. Cosine, a little tougher this time. Square root of 21 over 5.
I
Tangent,
have a recommendation.
what are your recommendation?
Why can't you do that? Just 2 over 3.
2 over 3?
That's one.
2 over 3?
It's not bad. It's pretty good. Reasonable.
Let's see.
You're saying that. Never mind.
2 over 4.
I want to say it.
Let's see, secant. Square root of 61 over 5. Cotangent. What do I want? This one. 5 over 13. Tangent. Okay. The tangent one, I'm going to put it up here, but I'm going to put a hint next to it. Tangent of 1.
Tangent of 1?
Mm-hmm. I'll only put the hint if somebody can tell me what it is before I put it up there. Yeah, just think of this as 1 over 1.
Smart.
And do it the same way. Or 2 over 2, or 3 over 3, whatever you got to do. Okay? And then sine, should I be mean? Nah. Yeah. Square root of 207 over 23. I like it. That'll be our 10 problems. Number 10 is, extra credit. Bonus. You could read like 10, you do 10.
10.
Oh, terrible. Good on Thursday. Make sure your assignment from yesterday is turned in, so it's hard, that's it.